Black holes are phenomena that have understandably captured the imagination of the general public recently, and if you know anything about them, that shouldn't come as a surprise. They are some of the biggest, most extreme, and above all coolest things that we have discovered yet in the entire universe. If you told a person a couple of centuries ago that there were vacuum-like entities the size of solar systems roaming the cosmos, you would probably either have been locked in a mental asylum or burned as a witch, depending on which century you said it in. These gargantuan voids of gravity are perhaps the most extreme, and as such the most interesting, astronomical phenomena in the entire universe, denying visualization, and causing mathematics to run screaming back to Newtonian physics. So, what exactly are these things?
One of the least understood concepts today is the relative emptiness of an atom because it's so counterintuitive. So for example, if an atom was scaled up to the size of a stadium, the nucleus would be the size of a golf ball in the very center of the stadium, and the electrons would be dust motes floating in the stands. The truth is, all interactions that we have with the world around us are simply forces and reactions occurring in vast clouds of emptiness, supported by minuscule particles.
Black holes occur when all of this space is forced out by an immensely powerful force, in this case gravity, and the center of the star becomes a point of infinite density composed of all the particles that were squished together. Stars are normally kept stable by the opposing forces of gravity and their own internal radiation pressure. When that pressure fails, when the star dies, three things can happen. First of all, if it has a mass less than 1.4 times our Sun's own, it turns into a red giant, a large, relatively cool ball of plasma. This is the death that our own Sun will experience, and it will become large enough to envelop the orbits of Venus, Earth, Mercury, and Mars. If the star's mass is between 1.4 and 2.8 times the mass of our Sun, it becomes a neutron star, a super-compressed soup of neutrons and fundamental particles, with an escape velocity that can reach up to half the speed of light. Finally, if the size of the star exceeds 2.8 times the mass of Sol, it becomes a black hole. As the incredibly powerful force of gravity draws the star inwards, the empty space within its atoms is forced out, and the neutron resistance force is overcome. All of the inconceivable mass of the star is compressed into an approximate sphere that ranges from the size of a planet to the size of an entire solar system. So, a good question is, why are black holes so dark? Well, it all relates back to the frizzy-haired genius that was Einstein. In 1905 and 1915 respectively, the titular physicist published his groundbreaking theories of special and general relativity. They involved some of the most complicated mathematics ever before seen, and their effects were so inconceivable that the majority of the population simply refused to believe them. Anyway, Einstein proposed large gravitational forces could bend light, normally considered a massless particle. Black holes occur when that concept is taken to its extreme. What if there was something that had a gravitational field so strong that it bent light so that it was drawn in and could never escape? Voila, the black hole was born. An object with gravity so great that it drew matter and energy in faster than anything in the universe could travel, beyond 3 times 10 to the 8 meters per second. Another offshoot of general relativity is that time, normally considered an absolute value of the universe, actually fluctuates around immense gravitational worlds. And, of course, for immense attractive forces, we need to look no further than our favorite voids of death. Black holes play host to some of the most drastic time dilation effects in the entire universe. Their prodigious gravity means that if an observer were to park next to a black hole and then fly back to Earth, they would be significantly younger than their counterpart. Imagine for a second that you're plummeting madly towards a black hole. To be honest, at this point you're pretty much dead, so you may as well enjoy the view while you're there. As you fell to your doom, your presumed suit may be able to identify the radiation streams that are flying past you. Radiation flying away from a black hole, you'd ask if you're a detached physicist and not a person preoccupied with their imminent death. How is this possible? That, my doomed friend, is Hawking radiation, and it is born of the interactions of particles on the quantum level around the black hole. The quantum world has a less than perfect reputation as being 1, incredibly difficult to understand, and 2, as counterintuitive as possible. We would normally think of space as empty and desolate, but at the quantum level it's actually a soup of madly interacting particles. Hawking radiation happens when two particles will spring to life where before nothing existed. Normally, these minute particles annihilate each other, but in very rare cases, one is pulled into the black hole and the other escapes, producing Hawking radiation.
And so we finally come to the most confounding part of a black hole, its singularity. The singularity is the center of the black hole, and when you reach it, all equations that we have break down. So far, we just have no idea what's in it. A break in the fabric of space-time? A wormhole even? In fact, physicists hypothesize that at the center of a black hole could be an entirely new universe, waiting for a single spark to trigger a new Big Bang. Honestly, we just don't know, and maybe we will never know. However, what is certain is that a singularity is by far the most extreme environment in the entire universe. As far as we can tell, time, space, gravity, and distance don't even exist when you get to it.
So, what have we learned about black holes? Well, for one, that they're incredibly scary. As in, it would be best to stay a couple billion kilometers away from them. Secondly, they are really, really, really complicated, incorporating quantum physics, relativity, and astrophysics difficult enough to cause grad students to start crying if it was on their exam. Thirdly, and finally, as scary as they are, it is also simultaneously impossible not to be awed by them. The largest, most extreme, most powerful phenomena in the entire universe. A sentiment most profoundly summed up by the physicist John Wheeler. The black hole teaches us that space can be crumpled like a piece of paper into an infinitesimal dot, that time can be extinguished like a blown out flame, and that the laws of physics that we regard as sacred, as immutable, are anything